For as long as most of us can remember, the speed of light has seemed like one of those rare facts that belongs in the same category as the number of hours in a day or the pull of Earth's gravity. It is simply there, a fixed feature of the universe that scientists have measured with astonishing precision. Light travels through empty space at just under 300,000 kilometers every second, crossing the distance from the moon in little more than a heartbeat, and reaching Earth from the sun in about 8 minutes. It feels like a number that was discovered, written into nature from the beginning, requiring no further explanation. Yet that comfortable certainty hides an extraordinary mystery. Science has become remarkably successful at describing what light does. It predicts how light bends around galaxies, how it escapes from distant stars, how it carries messages from the earliest moments after the Big Bang, and even how it ripples through optical fibers beneath oceans to connect continents, again and again. Experiments confirm the same remarkable limit. No signal carrying information has ever been observed outrunning light in a vacuum. Across laboratories and across billions of light years, the same value quietly appears. But knowing a number is not the same as knowing why that number exists. Why should the universe possess a maximum speed at all? Why not something faster, slower, or perhaps no universal limit whatsoever? Is this famous constant and independent law of nature? Or is it merely the visible consequence of deeper rules that remain hidden beneath our current understanding if space itself is not truly empty? Could the answer lie within the fabric of the vacuum that fills every corner of the cosmos? These questions have occupied generations of physicists, from the architects of electromagnetism to the pioneers of relativity and the explorers of quantum theory. Each breakthrough has brought remarkable clarity, yet each has also uncovered new layers of uncertainty. The more carefully we study light, the more it seems to illuminate not only the universe around us, but also the boundaries of our own knowledge. And perhaps the greatest surprise is that the speed of light may tell us less about light itself than about the very nature of space, time, and reality. Before asking where this remarkable limit comes from, we must first understand how humanity discovered that such a limit existed at all. Long before anyone knew how fast light travelled, many believed that its journey required no time at all. A lamp was lit, a star appeared in the night sky, lightning flashed across distant clouds, and the illumination seemed immediate. Human senses offered no hint that light was moving through space. It simply appeared wherever there was something to be seen, for centuries. This impression seemed perfectly reasonable. The ancient Greek philosopher Aristotle argued that light travelled instantaneously. The idea fit naturally with everyday experience, and there was little reason to question it. Even later thinkers, including Johannes Kepler, focused more on how light behaved than on how quickly it moved. If light possessed a speed, it had to be so immense that no observation of the time could reveal it. The first serious challenge came in the 17th century, when the Danish astronomer Ole Rømer turned his attention not to light itself, but to one of Jupiter's moons. Rømer was studying Io, a volcanic whirl that disappears regularly behind Jupiter before emerging once again. These eclipses occur with remarkable regularity, making Io something like a celestial clock. If light reached Earth instantly, the timing of these eclipses should remain perfectly predictable regardless of where Earth happened to be in its own orbit around the Sun. But they did not. When Earth moved farther from Jupiter, the eclipses appeared slightly delayed. When Earth moved closer again, they occurred earlier than expected. The moon itself had not changed its rhythm. Instead, something else was taking longer. Rømer proposed a daring explanation. The delay came from light needing time to cross the additional distance between Jupiter and Earth. It was a subtle effect, measured in minutes across hundreds of millions of kilometers, but it represented one of the first pieces of evidence that light does not travel infinitely fast. The exact value Rømer calculated was not perfectly accurate by modern standards. The distances between planets were not yet known with great precision, limiting the calculation, yet his reasoning was profound. For the first time, humanity possessed convincing evidence that light had a measurable speed. Over the following centuries, scientists sought increasingly precise ways to determine that speed. In the 19th century, Hippolyte Fizeau devised an ingenious experiment using a rapidly spinning toothed wheel. A beam of light passed through one gap in the wheel, travelled several kilometres to a distant mirror, and returned. If the wheel rotated at just the right speed, a tooth blocked the returning beam before it could pass back through the same opening. By measuring the wheel's rotation, Fizeau estimated how quickly light had completed its journey. Soon afterward, Léon Foucault improved upon the method by replacing the toothed wheel with a rotating mirror. His technique reduced uncertainties and revealed an even more accurate value. Decades later, Albert Michelson refined these measurements further, dedicating much of his scientific career to determining the speed of light with extraordinary precision. His experiments eventually reached accuracies that earlier generations could scarcely imagine. By the 20th century, the value had become one of the most carefully measured quantities in all of science. Today, the speed of light in a vacuum is defined as exactly 299,792, 448 meters per second. The precision is so great that modern science no longer measures this speed directly. Instead, the meter itself is defined by the distance light travels during a specific fraction of a second. Rather than asking how fast light moves, we now define part of our system of measurement around its motion. That remarkable shift reveals how deeply this constant has become woven into physics. It is no longer simply another experimental result. It serves as one of the foundations upon which our measurements of space and time are built. Yet an important distinction often goes unnoticed. Measuring a quantity with extraordinary accuracy does not explain why nature chose that value. Astronomers know the masses of planets with astonishing precision, but that does not explain why those planets formed with exactly those masses. Physicists can measure the electric charge of an electron to many decimal places, but the origin of that charge remains a deeper question. Precision and explanation are not the same thing. The same is true for the speed of light. Every experiment tells us what the value is. None tells us why the universe possesses this particular limit instead of another. At first glance, it is tempting to imagine light behaving like any ordinary object. A runner moves faster with stronger muscles, an airplane flies faster with more powerful engines, a spacecraft accelerates when larger rockets push against it. Speed appears to depend upon the object itself. Light refuses to fit that intuition. Whether produced by a candle, a laser, a distant quasar, or an exploding supernova, light always travels through empty space at exactly the same speed. A tiny flashlight and one of the brightest galaxies in the observable universe produce photons that obey the same cosmic limit. This constancy is unlike almost anything else in everyday experience. Even more curious, observers moving relative to one another continue to measure the same speed. A spacecraft racing through the solar system and an observatory resting quietly on Earth both find that light in a vacuum travels at exactly the same value. Common sense would suggest that motion should alter the measurement. Much as a passenger walking through a moving train has one speed relative to the train and another relative to the ground, light refuses to cooperate with that familiar picture. The deeper scientists examined this strange behavior, the more they realized that the mystery did not lie in light alone. The mystery reached into the very concepts of distance, duration, motion, and the structure of reality itself. The careful measurements of Römer, Fizeau, Foucault, and Michelson had established one extraordinary fact. They had measured a universal limit with increasing precision, but they had also uncovered a puzzle that measurement alone could never solve. Why should every observer, everywhere in the universe, always find exactly the same speed? That simple question would eventually force physicists to rethink space, time, and even the meaning of motion itself. The remarkable precision with which scientists measured the speed of light should, in principle, have brought a sense of closure. Nature had revealed one of its constants. The number could be written into textbooks, confirmed by experiment after experiment, and used to build ever more accurate descriptions of the physical world. Instead, it became the beginning of an even deeper puzzle. Throughout most of the 19th century, physicists viewed light as a wave. Every known wave required something through which to travel. Ocean waves move through water. Sound waves travel through air. Vibrations ripple through strings or solid materials. It seemed almost impossible to imagine a wave existing without a medium. If light was indeed a wave, what was waving? The proposed answer was something called the luminiferous ether, according to this idea. All of space was filled with an invisible substance so subtle that planets could pass through it without resistance, yet rigid enough to support electromagnetic waves. It was thought to be everywhere, extending from Earth's atmosphere to the most distant stars. The ether appeared to solve several problems at once. It explained how light could travel across empty space while preserving the familiar intuition that every wave must have something beneath it. For a time, the idea seemed perfectly reasonable, if the ether filled the universe. However, Earth could not remain stationary within it. Our planet circles the Sun at roughly 30 kilometers every second. The solar system itself orbits the center of the Milky Way. The galaxy moves through an expanding universe. Earth should therefore be drifting continuously through this invisible medium. That motion ought to produce a measurable effect. A helpful comparison comes from everyday travel. Someone riding a bicycle on a calm day experiences still air. Ride at the same speed into a headwind, and the air feels much stronger. Turn around and ride with the wind, and it feels weaker. The motion of the cyclist combines with the motion of the surrounding air. Physicists expected something similar for light. If Earth moved through the ether, then light travelling in the direction of Earth's motion should behave slightly differently from light travelling perpendicular to it. The differences would be incredibly small, but by the late 19th century, experimental techniques had become sensitive enough to search for them. Among the scientists determined to find this effect were Albert A. Michelson and Edward Morley. Their experiment, first performed in 1887, remains one of the most celebrated in the history of physics, not because it confirmed expectations, but because it quietly refused to do so. Michelson designed an instrument known as an interferometer. A beam of light was split into two identical parts. One beam travelled along one direction, while the second travelled at right angles. Mirrors reflected both beams back to their starting point, where they were reunited. If one beam experienced even a tiny delay because Earth was moving through the ether, the returning light waves would no longer line up perfectly. They would create an interference pattern that shifted as the apparatus rotated. The expected shift was small but measurable. Michelson and Morley rotated the instrument repeatedly, searching for changes as Earth moved through space. They repeated their observations with extraordinary care, accounting for temperature, vibration, and every source of experimental uncertainty they could identify. The shift never appeared. The result was astonishing. According to the experiment, light travelled at the same speed in every direction, regardless of Earth's presumed motion through the ether. At first, many physicists suspected that something had gone wrong. Perhaps the apparatus lacked sufficient precision. Perhaps the ether somehow flowed around Earth. Perhaps matter itself contracted slightly while moving through the ether, cancelling the expected effect. Several increasingly complicated explanations were proposed to rescue the old picture. Each solved one difficulty while creating another. Rather than questioning the existence of the ether itself, scientists searched for ways to preserve it. This tendency reflects an important feature of science. Ideas that explain many observations are rarely abandoned after a single unexpected result. Instead, researchers examine every possible alternative. They repeat experiments, improve instruments, and test competing explanations. Only when evidence continues pointing in the same direction does the scientific community gradually reshape its understanding. That process unfolded over several decades. Improved versions of the Michelson-Morley experiment continued to produce essentially the same outcome. As experimental accuracy increased by orders of magnitude, no convincing evidence for Earth's motion through an ether ever emerged. The invisible medium that had once seemed indispensable became increasingly difficult to defend. Yet removing the ether left physicists facing a profound question. If light required no medium, what exactly was propagating across empty space? The answer was far from obvious. Around the same period, another revolution was quietly taking shape through the work of the Scottish physicist James Clerk Maxwell. Maxwell had combined electricity and magnetism into a single mathematical framework. His equations revealed that changing electric fields naturally generate magnetic fields, while changing magnetic fields generate electric fields in return. Together, these fields could sustain one another. An electromagnetic wave, according to Maxwell, did not require vibrating particles like sound moving through air. Instead, the electric and magnetic fields continuously regenerated each other as they travelled. This was an extraordinary insight. Light itself appeared to be an electromagnetic wave. Even more remarkable, Maxwell's equations predicted the speed at which these waves should move, using measurements of two fundamental electrical properties of empty space, known today as the vacuum permittivity and vacuum permeability. The equations produced a value astonishingly close to the measured speed of light. For the first time, the speed of light emerged naturally from deeper physical relationships rather than existing as an isolated experimental fact. To many scientists, this seemed like the long-awaited explanation. But another mystery immediately appeared. Those electrical constants describe the vacuum itself. Why should empty space possess such properties? And why should they combine to produce exactly this speed? The equations were immensely successful. They predicted radio waves before they were discovered. They explained visible light, infrared radiation, ultraviolet light, X-rays, and gamma rays as members of one electromagnetic family. Their predictive power remains one of the greatest triumphs in all of science. Yet equations describe patterns. They do not always reveal ultimate causes. One can calculate the orbit of a planet without knowing why gravity exists in the first place. Likewise, Maxwell's equations explained how electromagnetic waves propagate. But they left open a deeper philosophical question. Why does the vacuum have precisely the characteristics required to produce this universal speed? As physicists wrestled with these questions, an even stranger realization slowly emerged. Perhaps the problem did not lie with light at all. Perhaps the assumptions about space and time themselves were incomplete. For centuries, space had been treated as an unchanging stage upon which the universe unfolded. Time flowed uniformly for everyone, everywhere. Distances were absolute. Durations were universal. The behavior of a light was beginning to suggest that these comforting assumptions might be the true illusion. If every observer measured exactly the same speed of light, regardless of their own motion, then something else had to give. The cracks in the old picture had widened enough that an entirely new understanding of reality was waiting just beyond them. At the close of the 19th century, physics appeared to stand on remarkably solid ground. Isaac Newton's laws described the motions of planets and falling apples with extraordinary precision. James Clerk Maxwell's equations unified electricity, magnetism, and light into a single elegant framework. New discoveries continue to refine the details, but many believed the foundations of the physical world had already been uncovered. Yet beneath this confidence, several quiet contradictions refused to disappear. The Michelson-Morley experiment had repeatedly failed to detect Earth's motion through the luminiferous ether. Maxwell's equations insisted that electromagnetic waves travelled at a specific speed determined by the properties of the vacuum. Newtonian mechanics, however, suggested that speeds should simply add together. These ideas could not all be correct simultaneously. For years, physicists searched for increasingly elaborate ways to preserve the existing picture. Some proposed that objects moving through the ether physically contracted. Others imagined that clocks somehow slowed as they travelled through space. These proposals were mathematically clever, but they felt like repairs added to an aging structure rather than a new foundation. The deeper question remained untouched. What if the assumptions themselves were wrong? One of the first people to appreciate the full significance of Maxwell's work was Maxwell himself. In the 1860s, while developing his famous equations, he discovered something extraordinary. The mathematics describing electric and magnetic fields naturally predicted the existence of waves travelling at a fixed speed. That speed depended only on two measurable properties of empty space, now known as the vacuum permittivity, denoted by E0, and the vacuum permeability, denoted by M0. When Maxwell substituted experimentally measured values into his equations, the calculated speed matched the measured speed of light with remarkable accuracy. He recognized the implication almost immediately. Light was not merely similar to an electromagnetic wave. Light was an electromagnetic wave. This realization transformed the understanding of light itself. What had once seemed like a mysterious substance emitted by luminous objects became a self-sustaining oscillation of electric and magnetic fields, capable of travelling across the apparent emptiness between stars. It was one of the greatest unifications in the history of science. Suddenly, visible light became just one small region within a much larger electromagnetic spectrum. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays all differed only in wavelength and frequency. They were not different phenomena, but different expressions of the same underlying field. The universe became richer and more interconnected than anyone had imagined. Yet Maxwell's equations also carried an unsettling message, unlike Newton's laws of motion, which naturally changed depending on the observer's velocity. Maxwell's equations always predicted exactly the same wave speed. There was no adjustment for an observer chasing the wave. There was no correction for someone moving away. The equation simply produced one constant. At first, many regarded this as a peculiarity of the mathematics. Surely the physical world would restore common sense once the ether was fully understood. Instead, every increasingly precise experiment reinforced Maxwell's prediction. Light behaved exactly as the equation suggested. The problem was no longer experimental. It had become conceptual. Into this landscape stepped a young patent examiner working in Bern, Switzerland. Albert Einstein was not surrounded by elaborate laboratories or expensive instruments. His daily work involved evaluating patent applications, many concerning clocks, electrical devices, and systems for synchronizing measurements across distances. These practical problems sharpened his appreciation for something physicists often took for granted. How do we know that two distant clocks show the same time? The question seems almost trivial. Suppose two observatories stand hundreds of kilometers apart. One flashes a signal toward the other, because light requires time to travel. Each observatory must carefully account for that delay when comparing their clocks. The more Einstein reflected on this, the more he realized that time itself could not be separated from the finite speed of light. In 1905, often called his miracle year, Einstein published a paper that would permanently reshape physics. Its starting point was astonishingly simple. He accepted two principles. The first was that the laws of physics should be the same for every observer moving at constant velocity. The second was that the speed of a light in a vacuum is the same for all such observers, regardless of the motion of the source or the observer. Today these statements appear familiar. At the time, they seemed almost impossible to reconcile. Consider two spacecraft drifting silently through interstellar space. One remains nearly at rest relative to Earth. The other travels at an enormous fraction of the speed of light. A beacon emits a flash. According to everyday intuition, the rapidly moving spacecraft should measure a different speed for that light than the stationary observer, just as one runner measures a different speed for another runner depending on whether they move together or apart. Einstein proposed something radically different. Both observers measure exactly the same speed. The consequence was extraordinary. If the speed remains fixed, then measurements of space and time themselves must adjust. Distances can no longer be absolute. Intervals of time can no longer be universal. Observers moving relative to one another experience different measurements of length and duration while agreeing on the speed of light. This was not a trick of perception. It was a property of reality itself. Time dilation, once an unimaginable concept, emerged directly from this reasoning. A moving clock genuinely ticks more slowly relative to a stationary observer. Likewise, length contraction naturally follows. Objects measured along the direction of motion become shorter from the viewpoint of another observer travelling at a different velocity. Neither effect is an illusion. Both have since been confirmed countless times through experiments involving atomic clocks, high-speed particles, satellites, and precision laboratory measurements. Even the global positioning system depends on correcting for these relativistic effects, without accounting for differences in the passage of time caused by both motion and gravity. GPS positions would drift by several kilometers each day. The technology guiding cars, aircraft, ships, and smartphones quietly relies upon Einstein's insights every second. Perhaps the most profound realization, however, was that space and time are not separate entities. Earlier generations imagined space as a vast three-dimensional stage through which time flowed independently. Einstein's theory united them into a single four-dimensional structure now called spacetime. Events possess positions not only in space but also in time, woven together into one continuous geometry. Light occupies a unique role within this geometry. Every observer, regardless of motion, constructs spacetime around the same invariant speed. The constant we call c is therefore more than the speed at which light travels. It is one of the conversion factors connecting space and time themselves. In modern relativity, c determines how intervals of distance relate to intervals of duration. It establishes the structure of cause and effect. It defines which events can influence one another and which remain forever disconnected. In this sense, the universe is not built around light. Rather, light faithfully reveals the geometry already present within space-time. This distinction is subtle but profound. The famous constant belongs not only to electromagnetism, but to the architecture of reality itself. And yet, even this revolutionary understanding leaves an important question unanswered. Relativity explains why every observer measures the same speed. It explains why space and time adjust to preserve that constancy. But it does not explain why that constant has precisely its observed value. Why should space-time possess this particular conversion factor instead of another? Why do the vacuum's electromagnetic properties produce exactly this limit? Einstein had transformed the question from one about moving beams of light into one about the very structure of the universe. The mystery had not disappeared. It had simply become much deeper. The answer, if one exists, might not lie in light alone, nor even in space-time itself, but in the seemingly empty vacuum through which every photon travels. The word vacuum has always carried a quiet simplicity. It suggests absence, an empty room after the furniture has been removed, a clear stretch of sky between distant clouds, a place where nothing remains. For centuries, that was almost exactly how physicists imagined the emptiness between the stars. The planets moved through vast regions where there appeared to be no air, no dust, and no visible substance. Light crossed those immense distances effortlessly. Gravity acted across them. Aside from an occasional wandering atom or grain of cosmic dust, interplanetary and interstellar space seemed to contain almost nothing at all. If the universe possessed a true stage upon which everything unfolded, surely this empty vacuum was it. Yet over the past century, that picture has changed so completely that modern physicists often hesitate to use the word empty, not because space is crowded with hidden matter, but because even perfect emptiness possesses structure. This transformation began gradually. As quantum mechanics emerged during the early 20th century, unlike classical physics, which often treats particles as tiny objects moving through otherwise passive space, quantum theory describes nature in terms of fields that extend everywhere. Every known fundamental particle is associated with its own quantum field. Electrons arise from the electron field. Photons emerge from the electromagnetic field. Quarks belong to quark fields. Similar descriptions exist for neutrinos and the other particles of the Standard Model. These fields are not confined to stars or planets. They fill all of space. Even in a region completely devoid of matter, the fields remain present. The vacuum, according to quantum theory, is therefore not the absence of fields. It is the lowest energy state those fields can occupy. That distinction may sound subtle, but it changes everything. A useful comparison comes from a calm lake. From a distance, the surface appears perfectly still, yet beneath that apparent stillness, countless water molecules continue moving. Tiny thermal motions persist even when the lake seems completely undisturbed. The quantum vacuum is not identical to this analogy, but it captures an important idea. Apparent stillness does not necessarily mean absolute inactivity. In quantum physics, the vacuum possesses fluctuations that arise naturally from the mathematical framework of the theory. These fluctuations are sometimes described in popular science as virtual particles, briefly appearing and disappearing. That language can be helpful as a simplified picture, but it should not be taken too literally. Virtual particles are not ordinary particles popping into existence where tiny cameras might someday observe them. Instead, they are mathematical features that appear in calculations describing how quantum fields interact. The deeper point is more important. The vacuum is capable of influencing measurable phenomena. One of the clearest examples is known as the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that two extremely smooth metal plates placed astonishingly close together in a vacuum would experience a tiny attractive force. At first glance, this seems almost impossible. No electric charge pulls the plates together, no magnet hides between them, no air pressure pushes them inward if the surrounding environment is also evacuated, yet the force exists. Modern experiments have measured it with impressive precision. The explanation involves the quantum electromagnetic field. Certain fluctuations fit differently between the plates than they do outside them, producing a minute imbalance that results in an observable attraction. The effect is extraordinarily small, noticeable only at microscopic distances, yet its importance is immense. It demonstrates that the vacuum cannot simply be dismissed as nothing. Empty space possesses measurable physical properties. Another remarkable phenomenon reinforces the same conclusion. According to quantum electrodynamics, often abbreviated as QED, an electron does not exist in complete isolation, even while traveling through empty space. Its surrounding electromagnetic field constantly interacts with the quantum vacuum. These interactions subtly alter measurable quantities, including the electron's magnetic properties and energy levels within atoms. One famous example is the Lamb shift, discovered by Willis Lamb in 1947. Hydrogen, the simplest atom in the universe, contains just one proton and one electron. Classical calculations predicted that certain electron energy levels should be exactly identical. Careful laboratory measurements revealed otherwise. The difference is tiny but unmistakable. Quantum electrodynamics successfully explains this shift as arising from interactions between the electron and the quantum electromagnetic field permeating the vacuum. Again, the lesson is not that particles emerge from nowhere in the everyday sense. Rather, the vacuum participates in the behavior of matter. It is an active component of physical reality, as experimental evidence accumulated throughout the 20th century. Physicists increasingly viewed empty space not as a blank canvas, but as a medium possessing well-defined quantum properties. This idea resonates in an unexpected way with Maxwell's 19th century equations. Recall that Maxwell found the speed of electromagnetic waves depends upon two measurable quantities describing the vacuum itself, the vacuum permittivity and the vacuum permeability, long before quantum theory existed. The equations had already hinted that empty space possesses physical characteristics. Quantum physics did not replace that insight. Instead, it enriched it. The vacuum became more than a passive backdrop with electrical constants. It became a sea of interacting quantum fields, whose properties influence the behavior of particles and radiation alike. Naturally, this invites a fascinating question. If light travels through a vacuum with measurable electromagnetic and quantum properties, could those properties determine the speed at which light propagates? At first glance, the idea seems appealing. After all, sound travels at different speeds through air, water, and steel because each medium possesses different physical characteristics. Could the vacuum be acting as a kind of cosmic medium? The comparison, however, must be handled carefully. Unlike sound, light does not require a material substance composed of atoms. The failure of the luminiferous ether and the success of relativity showed that there is no preferred material frame filling the universe through which light moves. The quantum vacuum is something entirely different. It does not define a universal state of rest. It does not allow observers to measure their absolute motion through space. Every observer moving uniformly still measures exactly the same speed of light, in full agreement with Einstein's relativity. This remarkable compatibility represents one of the greatest achievements of modern theoretical physics. Quantum electrodynamics and special relativity, though developed from different starting points, fit together with extraordinary precision. Their combined predictions have been tested to astonishing accuracy, making QED one of the most successful scientific theories ever constructed. And yet success does not always mean completeness. Physicists can calculate how quantum fields modify the behavior of particles with extraordinary precision. They can predict the outcomes of laboratory experiments to many decimal places. They can describe how photons interact with electrons, how electromagnetic waves propagate, and how quantum fluctuations influence atomic systems. But one deeper question quietly survives beneath all these accomplishments. Why does the quantum vacuum possess exactly the properties that it does? Why do its electromagnetic characteristics correspond to this particular value of delta C? Could those properties themselves emerge from an even deeper layer of reality? Or are they simply fundamental facts that admit no further explanation? Modern physics has not reached a consensus. Some researchers regard the vacuum's properties as basic ingredients of the universe, requiring no deeper cause within our current theories. Others suspect that these familiar constants may eventually arise from a more comprehensive framework that unifies quantum mechanics with gravity. At present, no experiment has definitively answered that question. The vacuum has become far richer than anyone living in Maxwell's or Einstein's time could have imagined. It is dynamic rather than empty, structured rather than featureless, observable rather than purely philosophical. Yet the more carefully scientists examine this invisible foundation of reality, the more another mystery begins to emerge. Perhaps the greatest puzzle is no longer whether the vacuum influences light. It is whether the vacuum itself is the final layer of nature, or merely the surface of something even deeper. The journey has gradually carried us from something that once appeared almost ordinary to a question that sits near the foundations of modern physics. We began with a number. Then we discovered that the number was not merely the speed of light, but a universal limit woven into the geometry of spacetime itself. We learned that empty space is not truly empty. It possesses measurable electromagnetic and quantum properties that influence the behavior of matter and radiation. We saw how Maxwell's equations naturally produce the speed of electromagnetic waves, and how Einstein's relativity elevates that speed into one of the defining features of reality. And yet, one question has remained quietly untouched. Why this number? Not approximately this number, not a number close to it. Exactly this one. This is the central mystery of our journey. It is also a useful reminder that science often answers one question by revealing another that is even deeper. For centuries, astronomers asked why the planets wandered across the sky. Newton's theory of gravity answered that question with extraordinary success, describing how masses attract one another and predicting planetary motion with remarkable precision. But Newton himself admitted that he did not know why gravity existed. More than 200 years later, Einstein explained gravity in an entirely different way, describing it not as a force but as the curvature of space-time produced by mass and energy. That insight transformed physics. Yet even general relativity does not explain why space-time responds to matter exactly as it does. The chain of explanations simply moved one level deeper. The speed of light occupies a similar place. Modern physics explains how it behaves with astonishing accuracy. It explains why all observers agree on its value. It explains how light propagates as an electromagnetic wave. It explains how this constant governs causality, energy, momentum, and the structure of space-time. But none of these achievements fully explain why the constant itself has the value that nature has chosen. This distinction is subtle but essential. There is a profound difference between describing a rule and explaining its origin. To see that difference, consider a familiar example from music. A piano has 88 keys. A musician can describe every note, every chord, and every melody that can be played on that instrument. The mathematics of sound can explain why certain combinations create harmony, while others produce tension. But none of that explains why the piano was built with exactly 88 keys instead of 87 or 90. The rules operate beautifully within the instrument, The deeper question concerns why the instrument has the form that it does. Physics faces an analogous challenge. Our theories describe the universe with extraordinary precision, but they begin with certain ingredients already in place. The speed of light is one of those ingredients. Several other constants share this mysterious status. The gravitational constant determines the strength of gravity. Planck's constant governs the scale at which quantum effects become important. The elementary electric charge sets the strength of electromagnetic interactions. The masses of fundamental particles determine the structure of atoms, stars, and galaxies. Each of these numbers is measured experimentally. Each appears fundamental within our current theories. None is predicted from deeper first principles by the standard model of particle physics. The speed of light belongs to this remarkable family. Some physicists therefore describe these quantities as fundamental constants of nature. The phrase is useful, but it should not be misunderstood. Calling something fundamental often means that our best current theories accept it as a starting point. It does not necessarily mean that no deeper explanation exists. History encourages caution. For centuries, atoms were considered indivisible. Later they were found to contain nuclei and electrons. Atomic nuclei were then shown to contain protons and neutrons. Protons and neutrons turned out to consist of quarks bound together by gluons. Each generation believed it had reached the fundamental layer. Each later discovered another beneath it. Whether today's constants occupy the deepest level remains unknown. This uncertainty has inspired one of the great ambitions of modern theoretical physics. Researchers hope to discover a framework from which today's seemingly independent constants emerge naturally. Rather than inserting their values by hand, the theory would predict them. Such a breakthrough would resemble Maxwell's unification of electricity and magnetism, or Einstein's unification of space and time. It would not merely describe nature more elegantly, it would explain why nature possesses its observed form. At present, however, no accepted theory has achieved this goal. String theory, for example, seeks to unify gravity with quantum mechanics by proposing that fundamental particles arise from tiny vibrating strings existing within additional spatial dimensions. Within some versions of the theory, the values of physical constants may depend upon the geometry of those hidden dimensions. This is an intriguing possibility, yet it remains speculative. No experimental observation has confirmed string theory as the correct description of reality. Another approach comes from loop quantum gravity, which attempts to quantize space-time itself rather than introducing new fundamental strings. Here too, researchers seek a deeper picture from which familiar space-time might emerge. Again, important mathematical progress has been made. Again, decisive experimental evidence remains absent. Other ideas investigate whether space-time itself could be an emergent phenomenon. Perhaps space and time are not fundamental ingredients at all, but collective behaviors arising from something even more basic, much as temperature emerges from the microscopic motion of countless molecules. If that were true, then the speed of light might also emerge from deeper relationships hidden beneath space-time. This possibility has attracted growing interest in several areas of theoretical physics, yet it too remains an active area of research rather than established scientific knowledge. These examples illustrate an important principle. Modern physics contains many promising ideas. Very few have yet crossed the demanding threshold from elegant mathematics to experimentally verified reality. That threshold matters. Science advances not by the beauty of its equations alone, but by their ability to survive confrontation with nature. For now, nature has remained remarkably quiet. Every increasingly precise experiment continues to support relativity. Every high-energy particle accelerator continues to confirm quantum electrodynamics. No observation has yet revealed that the speed of light changes with direction, location, or the motion of the observer. No measurement has uncovered a hidden mechanism operating beneath the familiar constant. If such a mechanism exists, it hides extraordinarily well. This situation places physicists in a fascinating position. They possess one of the most successful scientific frameworks ever developed. Its predictions guide satellites, particle accelerators, lasers, and astronomical observatories with astonishing accuracy. Yet one of its most familiar constants still resists deeper explanation. That is not a failure, it is a frontier. Perhaps the most remarkable feature of science is not that it answers every question. It is that it recognizes which questions remain open. The origin of the speed of light belongs firmly within that category. It is not a mystery because physicists lack ideas. It is a mystery because none of those ideas has yet earned the authority that only observation can provide. The next step, therefore, cannot come from philosophy alone. It must come from evidence. If a deeper explanation exists, traces of it should be written somewhere within the universe itself, waiting to be measured with sufficient care. The challenge is learning where to look, and understanding what nature is quietly trying to tell us. Every scientific mystery eventually arrives at the same quiet question. What can nature actually tell us? Ideas may be elegant. Equations may possess extraordinary mathematical beauty. Entire theories may fit comfortably within our intuition. But in astronomy and physics, none of these qualities is enough. The universe is under no obligation to behave according to human expectations. Only observation has the final word. The search for the origin of the speed of light is no exception. If there truly exists a deeper mechanism governing this universal constant, it should leave traces somewhere in nature. Those traces may be unimaginably subtle, but they must ultimately reveal themselves through measurements rather than imagination. The challenge is that the speed of light is almost unimaginably large, astonishingly stable, and woven into nearly every law of modern physics. Looking for evidence that explains it is rather like trying to understand the architecture of an entire cathedral by examining a single stone. Every measurement contains information, but no single observation reveals the whole structure. Instead, scientists gather clues from many different corners of the universe. Each clue answers one question while opening another. One of the simplest approaches begins in the laboratory. Modern physics has developed instruments capable of measuring time with extraordinary precision. Optical atomic clocks now lose or gain less than a second over many billions of years, making them among the most accurate devices humanity has ever built. These clocks rely on the predictable frequencies of light emitted or absorbed by atoms. If the speed of light or other fundamental constants were changing even slightly over time, those frequencies would shift in measurable ways. Physicists compare different kinds of atomic clocks continuously, searching for tiny discrepancies. Year after year, the comparisons agree within incredibly small uncertainties. The evidence strongly suggests that the fundamental relationships governing light remain remarkably stable under laboratory conditions. But laboratories observe only a tiny corner of space and an exceedingly brief moment in cosmic history. The universe offers a much larger laboratory. Every night, telescopes collect photons that have travelled for millions or even billions of years before reaching Earth. Some of the light entering modern observatories began its journey long before multicellular life appeared on our planet. Each photon is therefore a messenger from another era of cosmic history. If the speed of light had been significantly different during those ancient epochs, astronomers might expect subtle changes in the spectra of distant galaxies and quasars. A spectrum is often described as a fingerprint of light. When atoms absorb or emit photons, they do so at specific wavelengths determined by quantum mechanics. Different chemical elements leave different patterns of lines across the spectrum. These patterns are so distinctive that astronomers can identify the composition of stars and galaxies from unimaginable distances. They also provide a sensitive test of fundamental physics. If the relationships governing electromagnetic interactions had changed over cosmic time, the positions of these spectral lines would change in characteristic ways. For decades, researchers have compared light from extremely distant quasars with laboratory measurements made on Earth. Some studies have reported tiny hints that certain fundamental constants, particularly the fine structure constant, might have varied slightly across space or time. These results attracted considerable attention because the fine structure constant depends partly on the speed of light along with other physical quantities. Yet the evidence remains inconclusive. Other research groups, using different telescopes and analysis techniques, have found no convincing variation at present. The broader scientific consensus is that no reliable observational evidence demonstrates that these constants have changed. The debate illustrates how science proceeds at its frontier. Interesting hints invite further investigation. they do not become accepted conclusions until independent observations consistently agree. So far, they have not. Another powerful source of evidence comes from pulsars. These extraordinary objects are the rapidly rotating remnants of massive stars that ended their lives in supernova explosions. Although only about 20 kilometers across, a typical pulsar contains more mass than the Sun compressed into an astonishingly small volume. As it spins, powerful beams of electromagnetic radiation sweep across space like the rotating beam of a lighthouse. Whenever one of those beams crosses Earth, radio telescopes detect an extremely regular pulse. Some pulsars rotate hundreds of times every second. Their timing is so stable that astronomers often compare them to cosmic clocks. If the speed of light behaved unpredictably while traveling across interstellar space, the arrival times of pulsar signals would reveal those changes. Instead, after carefully accounting for known effects such as the motion of Earth, the influence of gravity, and the interstellar medium, the pulses remain astonishingly consistent. Their remarkable regularity strengthens confidence that light propagates through the vacuum in exactly the manner predicted by relativity. The same principle extends across even greater distances. When a distant supernova explodes, it releases enormous amounts of light spanning many wavelengths. Different wavelengths travel together across millions of light years. If empty space caused different colors of light to move at substantially different speeds in a vacuum, those signals would gradually separate during their long journey. Astronomers carefully search for such dispersion. While ordinary matter, such as interstellar plasma, can delay certain radio frequencies, these effects are well understood and can usually be distinguished from propagation through the vacuum itself. After accounting for known influences, light of different wavelengths continues to behave in accordance with Maxwell's equations and Einstein's relativity. Perhaps the most dramatic test arrived through an entirely new kind of astronomy. For centuries, humans explored the cosmos using electromagnetic radiation alone. Visible light, radio waves, infrared radiation, X-rays, and gamma rays all belong to the same electromagnetic family. Then, in 2015, the first direct detection of gravitational waves opened an entirely different window onto the universe. Produced by accelerating massive objects such as merging black holes and neutron stars, gravitational waves are tiny ripples in space-time itself, according to Einstein's general relativity. These waves should also propagate at the universal speed c. An extraordinary opportunity emerged in 2017. Astronomers observed the collision of two neutron stars in a galaxy approximately 130 million light-years away. The event, known as G7-Oid 7, produced both gravitational waves and electromagnetic radiation. The gravitational wave signal reached Earth first. Less than 2 seconds later, gamma rays from the same event arrived. Considering that both signals had travelled for roughly 130 million years, a difference of only a few seconds is remarkably small. Most of that tiny delay is believed to arise from processes occurring within the merger itself, rather than from different propagation speeds through space. The observation provided one of the strongest confirmations yet that gravitational waves and light travel at essentially the same cosmic speed. This result eliminated numerous speculative theories predicting significant differences between them. Again, the evidence narrowed the possibilities. It did not solve the deeper mystery. Particle accelerators provide another perspective. Facilities such as the Large Hadron Collider accelerate particles to velocities astonishingly close to the speed of light. As their energies increase, something remarkable happens. Their speeds increase less and less, instead of exceeding the speed of light. Additional energy primarily increases the particle's relativistic energy and momentum. No matter how much energy is supplied, particles possessing mass never quite reach c. This behavior has been confirmed countless times. It agrees precisely with special relativity. The speed of light continues to act as an unbroken limit. Together, these observations paint a remarkably consistent picture. Atomic clocks, spectroscopy, pulsars, supernovae, gravitational wave observatories, particle accelerators. Each probes a different aspect of reality. Each employs different instruments. Each operates on vastly different scales. From microscopic quantum systems to galaxies hundreds of millions of light-years away, yet all point toward the same conclusion. The speed of light appears extraordinarily stable. It does not fluctuate randomly. It does not vary with direction. It does not depend upon the motion of the observer. It behaves exactly as modern physics predicts. Ironically, this overwhelming success creates its own challenge. If the speed of light truly emerges from a deeper layer of reality, that underlying mechanism must reproduce these observations with astonishing precision. Any new theory must explain not only why the constant exists, but also why every experiment ever performed has measured the same value within extraordinary limits. Nature has given physicists an abundance of evidence. What it has not yet given them is the explanation that ties every piece together. The observations have become increasingly clear. The mystery has become increasingly focused. And now, having followed the evidence as far as it presently reaches, we arrive at a place where observation alone can no longer choose among several intriguing possibilities. The next step belongs to theory. When evidence reaches its limits, science does not come to a halt. It becomes more careful. The observations gathered over the past century tell a remarkably consistent story. Light travels through a vacuum at the same speed for every observer. Maxwell's equations describe electromagnetic waves with extraordinary accuracy. Einstein's theories of relativity explain why that speed remains invariant across every inertial frame. Quantum electrodynamics predicts the interactions of light and matter more precisely than perhaps any other theory in science. These achievements are among the greatest successes in the history of physics. Yet they leave one question unanswered. Why is the speed of light what it is? Because no experiment has yet provided a definitive answer. Physicists have explored several different possibilities. Some are firmly rooted in accepted theory. Others remain mathematical proposals awaiting experimental support. Distinguishing between them is essential. The first perspective is the one most widely accepted today. According to modern relativity, asking why light travels at the speed c may not be the deepest question at all. Instead, c is understood as a fundamental property of spacetime itself. This idea is subtle because everyday language naturally encourages a different picture. We speak about light moving through space, as though space were a stage and light were an actor crossing it. Relativity reverses that relationship. The geometry of spacetime already contains a built-in causal structure. Every event possesses what physicists call a light cone, separating events that can influence one another from those that cannot. The speed c defines this structure. Light does not choose the limit. Rather, light follows the geometry that already exists. From this viewpoint, the famous constant is not primarily a property of photons. Any massless particle, if one exists, would travel at exactly the same speed. Indeed, gravitational waves, which are not electromagnetic phenomena at all, propagate at essentially the same limit. This strongly suggests that c belongs to spacetime itself rather than to light alone. The strength of this explanation lies in its extraordinary agreement with observation. Special and general relativity have survived every experimental challenge placed before them. Their predictions guide technologies ranging from GPS satellites to particle accelerators. Their mathematical consistency is unmatched. Yet even here, one may still ask another question. Why does spacetime possess precisely this geometry? Relativity describes the structure. It does not necessarily explain why nature chose that particular structure instead of another. For many physicists, that deeper question remains open. A second perspective begins with Maxwell rather than Einstein. Recall that Maxwell's equations predict the speed of electromagnetic waves using two measurable properties of the vacuum, its permittivity and permeability. One can write the relationship symbolically as c equals m. This equation is one of the most famous in classical physics. It appears to suggest that the speed of light emerges naturally from the electromagnetic properties of empty space. At first glance, this seems like an explanation. If the vacuum possesses these particular properties, then the speed follows automatically. The difficulty is that the equation simply shifts the mystery. Why does the vacuum possess exactly those values of E0 and ME? Classical electromagnetism accepts them as experimentally measured quantities. It does not derive them from deeper principles. Thus, Maxwell's framework beautifully explains how electromagnetic waves propagate once those properties are known, but not why the vacuum has those properties in the first place. The explanation becomes more descriptive than ultimate. Quantum field theory offers another layer. In this framework, the vacuum is not merely characterized by two electromagnetic constants. It is the ground state of interacting quantum fields extending throughout all of space. Photons move through this quantum vacuum while interacting in subtle ways with other fields. These interactions can slightly modify the behavior of light under extreme conditions. For example, in extraordinarily intense electromagnetic fields, quantum electrodynamics predicts tiny nonlinear effects that are absent from Maxwell's original equations. Experiments continue searching for these rare phenomena. Importantly, these effects do not imply that the ordinary vacuum behaves like a material substance through which light must push its way. Instead, they reveal that quantum fields possess an intricate internal structure. Some theorists therefore wonder whether the familiar constants describing the vacuum might themselves emerge from deeper quantum relationships not yet fully understood. This possibility remains scientifically plausible, but no accepted theory has yet demonstrated how to derive the observed value of C from first principles. The evidence is therefore incomplete. Another family of ideas explores whether spacetime itself is emergent. This proposal represents one of the more intriguing directions in contemporary theoretical physics. To appreciate it, consider a snowflake. Its beautiful hexagonal pattern is real. Yet no single water molecule possesses that shape. The pattern emerges collectively from the interactions of countless molecules. Likewise, the smooth surface of an ocean emerges from unimaginable numbers of individual water molecules moving beneath it. Temperature provides another familiar example. No individual molecule contains temperature. Temperature describes the collective behavior of enormous numbers of particles. Some physicists ask whether space-time could resemble these examples. Perhaps space and time are not fundamental ingredients of reality. Perhaps they emerge collectively from something deeper that is not itself spatial or temporal in the ordinary sense. If that were true, then the speed of light might also be an emergent property. Rather than being inserted into the laws of physics, it would arise naturally from the microscopic structure beneath space-time. This idea appears in several research programs, though often in very different mathematical forms. Some versions involve quantum entanglement playing a foundational role. Others investigate networks, information theory, or discrete quantum geometries. These approaches are intellectually rich, yet it is important to emphasize their present status. They remain active areas of theoretical research. None has yet achieved broad experimental confirmation. Without observational evidence, they remain hypotheses rather than accepted theories. String theory approaches the mystery from another direction. Instead of treating particles as dimensionless points, string theory proposes that the elementary constituents of nature are tiny vibrating strings existing in additional spatial dimensions. Different vibrational patterns correspond to different particles. Within some versions of the theory, the values of physical constants depend upon the geometry of the compact extra dimensions. If this picture proved correct, the speed of light might ultimately be traced back to the underlying geometry of those hidden dimensions. Again, this is a fascinating possibility. Again, decisive experimental evidence has not yet arrived. The same caution applies to numerous speculative models proposing varying speeds of light in the very early universe. A small number of cosmological theories suggest that conditions shortly after the Big Bang may have differed from those observed today. Some versions propose that an effective speed associated with causal processes could have behaved differently during those earliest moments. Such models attempt to address certain cosmological puzzles, including the remarkable uniformity of the cosmic microwave background. However, these ideas remain highly speculative. They compete with inflationary cosmology and other well-developed frameworks. No observation has yet established that the speed of light itself truly changed in the early universe. Distinguishing between an effective description and a genuine variation of the fundamental constant is also subtle and model-dependent. The debate remains unresolved. Stepping back, a clear pattern begins to emerge. Theories occupy different levels of confidence. Certain statements belong among observed facts. The speed of light in a vacuum is extraordinarily stable. Every inertial observer measures the same value. Gravitational waves propagate at essentially the same limit. These conclusions rest upon extensive experimental evidence. Other statements belong among accepted theories. Special relativity, general relativity, quantum electrodynamics. These frameworks explain enormous ranges of observations with exceptional accuracy. Still other ideas remain hypotheses: emergent spacetime, string theory, loop quantum gravity, various models of varying constants. Each seeks a deeper explanation. Each has produced valuable mathematical insights. None has yet been confirmed as the definitive description of nature. That distinction is not a weakness. It is one of science's greatest strengths. Physics does not hide uncertainty behind confident language. It separates what has been observed from what has been inferred and what has merely been imagined. This discipline allows knowledge to grow steadily without losing its reliability. For now, the evidence supports a remarkable conclusion. The speed of light behaves as though it is woven into the fabric of reality itself. Whether that fabric is truly fundamental, or whether it rests upon an even deeper foundation still waiting to be discovered, remains one of the most profound open questions in modern science. And if one particular possibility were true, its consequences would reshape our understanding of the entire universe. One possibility appears again and again, although in many different forms. It does not claim that Einstein's relativity is wrong. It does not deny Maxwell's equations. Nor does it suggest that the countless experiments confirming the constancy of the speed of light have somehow been misunderstood. Instead, it asks a quieter question. What if all of those theories are describing the same deeper reality from different directions? More specifically, what if the properties of the quantum vacuum are not simply background conditions, but the reason that space-time exhibits the behavior we observe? This idea remains speculative. There is no accepted theory demonstrating that the quantum vacuum determines the value of C. Nevertheless, it provides a scientifically motivated thought experiment because it builds directly upon concepts already established in modern physics. The exercise is not intended to predict the future. Its purpose is to explore the consequences of a possibility that many physicists have considered in one form or another. To begin, it helps to return to a familiar observation. When we think about waves in everyday life, their speed depends on the medium through which they travel. A ripple moves differently across a quiet pond than across a stormy sea. Sound travels much faster through steel than through air because the microscopic structure of each material responds differently to vibrations. The wave does not choose its speed. The material determines it. Light is fundamentally different. It does not move through a material medium made of atoms. The failure of the luminiferous ether and the success of relativity showed that there is no universal substance defining absolute rest. Yet modern quantum theory tells us that the vacuum possesses measurable properties. It is not a featureless void. It contains quantum fields extending throughout the universe. If those fields possess a particular structure, could they define the behavior of electromagnetic waves in a way that resembles a medium without actually being one? This distinction is crucial. The quantum vacuum would not function like air or water. There would be no preferred direction, no cosmic wind, no absolute frame against which motion could be measured. Every observer moving uniformly would still describe the same laws of physics, exactly as relativity requires. The medium, if that word is even appropriate, would exist only in the sense that space-time itself possesses intrinsic physical properties. This possibility becomes slightly easier to picture through another comparison. Consider a crystal. From a distance, its surface appears perfectly smooth. Under a microscope, however, it consists of atoms arranged in a highly organized pattern. Many large-scale properties of the crystal, including the way vibrations travel through it, emerge from that microscopic arrangement. The vibrations are real, the crystal is real, yet the speed of those vibrations ultimately reflects the deeper structure beneath the visible surface. Some theoretical physicists ask whether spacetime could behave in a broadly analogous way. Not because spacetime literally consists of atoms. No experiment has demonstrated such a thing. Rather, they wonder whether the smooth geometry described by Einstein might emerge from microscopic relationships that remain hidden at accessible energies. If so, the speed of light could also be an emergent quantity. It would appear perfectly constant because the deeper structure itself possesses extraordinary uniformity throughout the observable universe. An interesting consequence follows immediately. The value of C would no longer be an arbitrary number inserted into the equations. Instead, it would arise naturally from the underlying architecture of reality. The relationship would resemble the way the elastic properties of a solid determine the speed of sound travelling through it. Again, the analogy has limits. Sound requires matter, light does not. The comparison concerns emergence, not mechanism. The distinction matters because careless analogies can easily become misleading. If spacetime truly emerged from deeper physics, what else might emerge alongside it? The answer reaches far beyond light alone. Distances themselves could become collective properties rather than fundamental ingredients. Time might also emerge from more primitive relationships. Even gravity, which general relativity describes as geometry, could represent a large-scale manifestation of microscopic processes hidden beneath everyday experience. These ideas are not entirely new. Over the past few decades, several independent areas of theoretical physics have begun hinting at similar possibilities. One example comes from black hole thermodynamics. During the 1970s, physicists including Jacob Bekenstein and Stephen Hawking discovered something extraordinary. Black holes behave as though they possess entropy. Entropy is commonly associated with the number of microscopic configurations underlying a physical system. A gas has entropy because its molecules can be arranged in many different ways while appearing identical on large scales. If black holes possess entropy, they may also possess microscopic degrees of freedom. Yet general relativity alone does not specify what those microscopic ingredients are. This observation suggested that spacetime itself might conceal an underlying structure not visible within Einstein's classical description. Another intriguing development arose from the study of quantum entanglement. Entanglement describes correlations between quantum systems that cannot be explained through ordinary classical intuition. Over time, some researchers noticed that patterns of entanglement appear closely connected with the geometry emerging in certain theoretical models. In a few highly specialized frameworks, changes in quantum entanglement correspond to changes in the geometry of spacetime itself. These results do not prove that spacetime is literally made of entanglement, nor do they establish the origin of the speed of light, but they hint that geometry and quantum information may be more deeply connected than once believed. Another consequence of the thought experiment concerns causality. Relativity teaches that the speed of light determines the maximum rate at which cause and effect can propagate. If C emerges from deeper microscopic physics, then causality itself may also emerge. This is an astonishing possibility. Rather than existing as a primitive rule of the universe, the very distinction between before and after across distant regions could arise from more fundamental relationships. Such ideas remain highly speculative. They should not be mistaken for established scientific conclusions. Nevertheless, they demonstrate how a single question about light naturally expands into questions about time, information, and the structure of reality itself. The thought experiment also reveals an important constraint. Any deeper theory must reproduce the extraordinary success of relativity. At the scales accessible to observation, space-time behaves with astonishing precision exactly as Einstein described. Any microscopic model predicting noticeable violations under ordinary conditions would already have been ruled out by countless experiments. This places severe restrictions on theoretical proposals. Whatever deeper structure exists, if one exists at all, it must become almost perfectly invisible on familiar scales. Physicists sometimes describe this as an effective theory. An effective theory need not describe the ultimate constituents of reality. Instead, it captures behavior at the scales where observations occur. Fluid dynamics, for example, successfully describes flowing water without tracking every individual molecule. Likewise, general relativity may accurately describe spacetime even if an underlying microscopic description eventually replaces it at unimaginably small distances. This perspective does not diminish Einstein's achievement. Newtonian gravity remains extraordinarily useful despite the deeper understanding provided by general relativity. Similarly, relativity would remain correct within its domain even if future discoveries uncovered another layer beneath it. The possibility carries profound implications for cosmology. If space-time and the speed of light emerge from deeper physics, then the earliest moments of the universe may have involved processes unlike anything described by our current theories. Near the Big Bang, where quantum effects and gravity become equally important, today's smooth space-time may not yet have existed in its familiar form, the distinction between space and time themselves might have been fundamentally different, our present equations becoming complete in precisely that regime. Here, the thought experiment reaches the edge of established science. Beyond this point, observation grows increasingly difficult. Mathematics becomes more speculative. Competing ideas multiply. Yet one lesson already stands out. The question, where does the speed of light really come from, may ultimately be inseparable from an even larger question. Where do space and time themselves come from? If those two mysteries share the same origin, then understanding one could transform our understanding of the other. And that possibility extends far beyond photons racing through empty space. It reaches outward to stars, galaxies, black holes, and the evolution of the entire cosmos, until now. Our journey has remained focused on the speed of light itself. We have explored laboratories, historical experiments, quantum fields, and the structure of space-time. Yet one of the most remarkable aspects of this constant is that it is not confined to any single branch of physics. It quietly shapes nearly every chapter in the story of the universe. The familiar value of approximately 300,000 kilometers per second is often introduced as a property of light in practice. It serves as one of the organizing principles of the cosmos, from the lives of stars to the evolution of galaxies, from the growth of black holes to the expansion of the observable universe. The same constant appears again and again. What first seemed like an isolated number gradually reveals itself as one of the threads holding the entire cosmic tapestry together. Perhaps the easiest place to see this is in the night sky itself. Whenever we look upward, we're also looking backward in time. This statement has become familiar, yet its meaning deserves a slower consideration. Light requires time to travel. When sunlight reaches Earth, it has already spent about 8 minutes crossing the space between our planet and its parent star. If the sun were somehow to disappear, ignoring the fact that such an event cannot occur instantaneously according to known physics, Earth would continue receiving sunlight for roughly 8 more minutes. The delay is not an illusion. It is built into the finite speed at which information propagates through space-time. The same principle extends outward. The nearest star beyond the Sun, Proxima Centauri, lies a little over 4 light-years away. Every photon arriving from that small red star began its journey more than 4 years ago. The bright star Vega appears as it was about 25 years in the past. The glowing clouds of the Orion Nebula reach us after more than 1,000 years of travel. The Andromeda Galaxy, our nearest large galactic neighbour, is seen as it existed roughly 2.5 million years ago. Long before the first members of our own genus walked across Africa, the most distant galaxies observed by modern telescopes are visible only because their light has spent more than 13 billion years travelling across an expanding universe. Astronomy is therefore unlike almost every other science. A geologist studies rocks that can be held in the hand. A chemist examines reactions occurring in the present. An astronomer rarely observes the universe as it is now. Instead, the sky becomes an archive of history. The speed of light creates that archive, without a finite propagation speed. Every region of the cosmos would appear simultaneously. There would be no natural record of cosmic evolution written across different distances. Ironically, the delay that limits our observations also makes astronomy possible. It allows scientists to reconstruct the history of stars and galaxies by looking progressively farther away. The universe has become its own historical document. The same constant also governs the lives of stars. Deep within stellar cores, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. Those reactions occur near the center of the Sun, approximately 700,000 kilometers beneath its visible surface. The photons produced there do not stream directly into space. Instead, they begin an astonishingly complicated journey. Within the Sun's dense interior, photons are repeatedly absorbed and re-emitted by charged particles. Each interaction changes their direction. Rather than travelling outward along a straight path, they perform what physicists describe as a random walk, although every individual movement occurs at the speed of light between interactions. The enormous number of collisions dramatically slows the overall escape. Current models suggest that energy generated near the solar core may require tens of thousands to hundreds of thousands of years to reach the visible surface. depending on the details of energy transport inside the Sun. Only after finally escaping into space does sunlight make the comparatively brief 8-minute journey to Earth. The contrast is striking. Crossing the vacuum between the Sun and Earth requires minutes. Escaping the interior of the Sun may require timescales comparable to the rise and fall of entire human civilizations. Again, the speed of light does not act in isolation. Its interaction with matter shapes the behavior we observe. On larger scales, galaxies tell a similar story. The Milky Way spans roughly 100,000 light-years. No signal traveling at or below the speed of light can cross the galaxy more quickly than that. This seemingly simple fact has enormous consequences. Suppose a civilization somehow existed simultaneously on opposite sides of the Milky Way. Even if both possessed technologies capable of transmitting perfectly efficient laser signals, a conversation would unfold at an almost unimaginable pace. A greeting sent from one side would require roughly 100,000 years to reach the other. The reply would not return for another 100,000 years. A single exchange would last longer than the entire history of modern Homo sapiens. The speed of light therefore imposes not only physical limits but also practical limits on communication across the cosmos. Distance becomes inseparable from time. The same principle governs the evolution of galaxies themselves. Changes occurring within one region cannot instantaneously influence another. Star formation, supernova explosions, and the motions of gas clouds all unfold within the causal limits established by relativity. The universe evolves locally before it evolves globally. Black holes reveal this relationship even more dramatically. One often hears that nothing can escape from a black hole, not even light. While broadly correct, this statement deserves careful interpretation. The defining feature of a black hole is its event horizon. This boundary marks the region beyond which every possible future path through spacetime leads inward. It is not that light suddenly becomes too weak to escape. Rather, spacetime itself is curved so profoundly that every direction available to light points deeper toward the center. Here again, the speed of light retains its universal value. A photon passing near a black hole always travels locally at c. What changes is the geometry through which it moves. General relativity replaces the idea of gravity pulling on light with a subtler picture. Spacetime itself determines the available paths. The behavior of light therefore becomes a map of gravitational geometry. Astronomers use this property every day. Massive galaxies bend light from more distant objects through gravitational lensing, producing arcs, rings, and multiple images across the sky. By measuring these distortions, researchers infer the distribution of visible matter and the far more abundant dark matter surrounding galaxies. Remarkably, light allows scientists to study substances that emit no light themselves. Dark matter remains one of the greatest unsolved mysteries in cosmology. It neither shines nor reflects electromagnetic radiation. Its existence is inferred through gravity. Yet because light faithfully follows the geometry created by mass, it becomes one of the most powerful tools for revealing where unseen matter resides. In this way, the speed of light contributes indirectly to one of astronomy's most important investigative techniques. Perhaps the largest stage upon which c performs its role is the expanding universe itself. According to modern cosmology, space has been expanding for approximately 13.8 billion years. At first glance, one might assume that this means the observable universe has a radius of exactly 13.8 billion light-years. The reality is more subtle, because space itself expands while light travels through it. The most distant galaxies whose ancient light reaches us today are now much farther away than 13.8 billion light-years. Current cosmological models estimate the radius of the observable universe to be roughly 46 billion light-years. This does not violate relativity. Nothing is travelling through space faster than light in the ordinary sense. Instead, the fabric of space itself expands, carrying distant galaxies farther apart. The distinction between motion through space and the expansion of space becomes essential. Again, the speed of light defines the structure of what we can observe. Everything beyond the observable universe lies outside our present cosmic horizon. Light from those regions has simply not had sufficient time to reach us since the beginning of cosmic expansion. Whether the universe extends infinitely beyond that horizon remains unknown. The horizon itself is created not by the limits of our telescopes, but by the finite speed at which information can travel. In every direction we have explored, the same pattern emerges: stars, galaxies, black holes, dark matter, cosmic expansion. Each depends fundamentally upon the existence of a universal causal limit. The speed of light is not merely another physical constant. It quietly determines how the universe grows, communicates, and reveals its own history. And yet, as these connections multiply, another realization begins to emerge. The same constant that links every corner of the cosmos also seems to unite ideas that once appeared completely unrelated: electromagnetism, gravity, quantum fields, information, geometry. Perhaps they are not separate stories after all. Perhaps they are different chapters within a single, deeper narrative that physics is only beginning to uncover. As our journey has unfolded, several ideas have appeared more than once. At first they seem to belong to different parts of physics. Maxwell's equations belong to electromagnetism. Einstein's relativity belonged to spacetime. Quantum mechanics described the microscopic world. Black holes seemed relevant only to gravity. The expanding universe belonged to cosmology. Each discipline developed its own language, its own experiments, and its own remarkable successes. For many decades, they appeared to be neighbouring provinces connected only by loose borders. Yet as modern physics has advanced, those borders have become increasingly difficult to draw. Again and again, discoveries made in one field quietly illuminate another. The speed of light lies near the centre of many of these unexpected connections. One of the most striking relationships involves something we rarely associate with light at all: information. At first glance, information seems almost abstract. A sentence in a book, a radio message crossing an ocean, a photograph stored on a computer. These examples appear far removed from photons travelling through interstellar space. Yet physics treats information in a surprisingly concrete way. Whenever information moves from one place to another, it must be carried by some physical process. That carrier might be a beam of light through an optical fibre. It might be radio waves crossing space. It could involve electrons flowing through a circuit or quantum particles travelling inside an experimental device. Whatever the method, information never exists independently of physical reality. This realization gradually transformed one of Einstein's most famous ideas. The speed of light is often introduced as the fastest speed that light itself can travel. A more precise statement is deeper. It is the maximum speed at which information and causal influence can propagate through space-time. This distinction explains several phenomena that otherwise appear mysterious. Suppose the sun could somehow vanish instantaneously. According to general relativity, this cannot occur through any known physical process. But as a thought experiment, it is instructive. Would Earth immediately drift away because the sun's gravity had disappeared? The answer is no. Just as sunlight requires about 8 minutes to reach Earth, any change in the sun's gravitational field would also require approximately 8 minutes to arrive. Gravity does not communicate instantaneously. Changes in space-time propagate outward at the same universal speed. The same principle governs gravitational waves. When two black holes spiral together and merge, the resulting distortion travels across the cosmos not as light, but as ripples in space-time itself. Yet those ripples still respect the same causal limit. Suddenly, electromagnetism and gravity begin to resemble different expressions of a common rule. Neither can transmit information faster than C. This shared behaviour hints at a deeper unity. Another unexpected connection appears within particle physics. The Standard Model describes every known elementary particle as an excitation of an underlying quantum field. Photons arise from the electromagnetic field. Electrons arise from the electron field. Quarks belong to quark fields. Each field extends throughout the entire universe. These fields are not isolated islands. They constantly interact. Electrons emit and absorb photons. Quarks exchange gluons. Weak interactions involve W and Z bosons. The Higgs field interacts with many fundamental particles, giving rise to their observed masses through the Higgs mechanism. Here another remarkable pattern emerges. Particles without mass travel at the universal speed c. Particles possessing mass always move more slowly. This observation is not simply a coincidence. Within relativity, mass changes how objects move through space-time. A massless particle naturally follows what physicists call a null trajectory. travelling at the invariant speed. Massive particles follow different paths, requiring energy to accelerate but never reaching that ultimate limit. The distinction becomes especially elegant when viewed geometrically. Light is not struggling to move quickly. It is following the natural paths permitted to massless excitations of space-time. This insight quietly links relativity with quantum field theory. Both describe the same limit from different perspectives. One emphasizes geometry. The other emphasizes quantum fields. Neither contradicts the other. Instead, they reinforce one another. The connections continue. Earlier, we encountered the vacuum as the ground state of quantum fields. General relativity, meanwhile, describes gravity as the curvature of space-time. At first, these ideas seem almost unrelated. One concerns microscopic fluctuations. The other governs planets, galaxies, and black holes. Yet the universe refuses to keep them separate. The clearest example appears near black holes. Stephen Hawking's famous prediction that black holes emit thermal radiation arises precisely because quantum fields exist within curved space-time. Neither quantum mechanics nor general relativity alone predicts Hawking radiation. The effect emerges only when both frameworks are considered together. Although direct observational confirmation of Hawking radiation from astrophysical black holes remains beyond current technology, because the predicted emission is extraordinarily weak. The theoretical prediction has profoundly influenced modern physics. It demonstrates that the boundary between gravity and quantum theory is not merely philosophical. Nature appears to require both. The same convergence appears in the early universe. According to the standard cosmological model, the observable universe began in an extremely hot, dense state during its earliest fractions of a second. Temperatures were so immense that quantum effects and gravity were simultaneously important. Unfortunately, this is exactly the regime where our current theories become incomplete. General relativity performs beautifully on cosmic scales. Quantum mechanics succeeds brilliantly on microscopic scales, where both become equally important. Physicists still lack a complete unified description. The speed of light sits quietly inside both frameworks. It belongs equally to Einstein's equations and to quantum field theory. Yet the two theories themselves remain only partially reconciled. This tension is sometimes described as one of the greatest unfinished tasks in theoretical physics. Perhaps no idea illustrates these hidden connections more beautifully than symmetry. Modern physics relies heavily upon symmetry principles. A symmetry does not merely describe visual balance. It refers to transformations that leave the fundamental laws unchanged. For example, the laws of physics appear identical today and tomorrow. They also appear identical regardless of where a laboratory is built, whether on Earth or aboard a spacecraft drifting through deep space. Special relativity introduces another profound symmetry. The laws remain the same for every inertial observer. The invariant speed c forms an essential part of that symmetry. Remove it, and the mathematical structure changes completely. Thus, the speed of light is not simply another measured constant. It helps define one of the deepest symmetries known in nature. Quantum field theory also depends critically upon symmetry. Gauge symmetries govern electromagnetic, weak, and strong interactions. The Higgs mechanism involves symmetry breaking. Entire families of particles arise because of underlying symmetrical structures within the equations. Again, different branches of physics converge upon similar organizing principles. Another surprising bridge connects light with entropy. Earlier we discussed black hole entropy. Entropy measures the number of microscopic configurations corresponding to a macroscopic state. During recent decades, researchers have increasingly realized that entropy, information, and space-time geometry may be more closely related than once imagined. Some theoretical developments suggest that Einstein's equations themselves may resemble thermodynamic relationships describing the large-scale behavior of underlying microscopic degrees of freedom. This idea remains an area of active research rather than settled science. Yet it reflects an important shift. Concepts once regarded as belonging to completely different disciplines now appear unexpectedly intertwined. Information, entropy, geometry, quantum fields, gravity, light. Each repeatedly points toward the others. Even cosmology has begun to reflect this growing unity. The cosmic microwave background, gravitational lensing, galaxy surveys, gravitational wave astronomy, and particle accelerators all investigate different questions. Yet together they constrain the same underlying laws governing reality. A measurement made beneath the mountains at CERN can influence theories describing the evolution of the entire observable universe. A distant galaxy observed by the James Webb Space Telescope may help refine models of particle physics developed in terrestrial laboratories. The scales could scarcely be more different. The principles connecting them continue to grow stronger. Perhaps this is one of the quietest lessons offered by modern astronomy. The universe is not assembled from isolated subjects. Its apparent divisions exist largely for human convenience. Nature itself does not separate electromagnetism from cosmology, or gravity from quantum theory. Those distinctions arise within our textbooks. Reality appears far more unified. The speed of light has served throughout our journey as a guide leading from one field into another. Each connection has made the mystery richer rather than simpler, and as the pieces continue fitting together, modern observatories and laboratories are beginning to explore these relationships with tools that previous generations could scarcely have imagined. The questions surrounding the speed of light have accompanied physics for more than a century. What has changed most dramatically is not the question itself, but the tools available to investigate it. Old Roma watched the eclipses of one of Jupiter's moons through a telescope that would appear remarkably simple beside modern observatories. Fizeau relied on a spinning-toothed wheel. Michelson built exquisitely precise optical instruments that pushed 19th century engineering to its limits. Einstein, perhaps most famously, required little more than careful reasoning supported by the experiments already available. Today's astronomers inherit all of that history. They also possess technologies that those earlier generations could scarcely have imagined. Some orbit far above Earth's atmosphere, others occupy mountaintops, deserts, and deep underground laboratories. Some listen for ripples in spacetime itself, others measure the ticking of atoms so precisely that the age of civilizations becomes almost insignificant. Each instrument approaches the same mystery from a different direction. One of the greatest revolutions has occurred in astronomy itself. For nearly 400 years, beginning with Galileo's telescope, observing the universe primarily meant collecting light. As telescopes grew larger, astronomers simply gathered more of it. The 20th century expanded that vision beyond visible wavelengths. Radio telescopes revealed cold clouds of hydrogen stretching across galaxies. Infrared observatories penetrated dusty stellar nurseries hidden from ordinary sight. Ultraviolet telescopes exposed the hottest stars. X-ray and gamma-ray observatories uncovered violent environments surrounding neutron stars and black holes. Although these instruments explored very different regions of the electromagnetic spectrum, they all relied upon the same fundamental messenger: light. The James Webb Space Telescope has extended this exploration farther than ever before in infrared wavelengths. By observing galaxies whose light has travelled for more than 13 billion years, Webb allows astronomers to examine the universe during its earlier stages of galaxy formation. Importantly, Webb has not measured a different speed of light. Instead, it provides increasingly detailed observations of conditions under which existing theories can be tested. Do the earliest galaxies behave as expected? Do their spectra match predictions based upon known atomic physics? Do observations remain consistent with the assumption that fundamental constants have remained stable across cosmic history? So far, Webb's discoveries continue to support the remarkable consistency of modern physics, while simultaneously raising new questions about galaxy formation and early cosmic evolution. It has deepened the mystery without overturning the foundations. Another powerful observatory approaches the problem from an entirely different perspective. The European Southern Observatory's Very Large Telescope, perched high in Chile's Atacama Desert, observes distant quasars whose light has crossed much of the observable universe. These quasars act like brilliant cosmic flashlights, as their light passes through clouds of gas lying between the quasar and Earth. Atoms within those clouds absorb very specific wavelengths. The resulting absorption lines become extraordinarily sensitive probes of atomic physics across billions of years. Researchers compare these ancient fingerprints with laboratory measurements performed on Earth. Any unexpected shift could indicate that certain fundamental constants have changed over cosmic time. Such investigations require extraordinary care. Tiny instrumental effects, calibration uncertainties, and the motions of intervening gas clouds can all imitate the signals researchers seek. Because of these challenges, individual studies occasionally appear to disagree. Some have reported intriguing hints of variation. Others have found none. The current scientific consensus remains cautious. No convincing evidence has yet demonstrated that the speed of light or closely related fundamental constants have changed during the observable history of the universe. The search continues because even a minute variation would transform modern physics. Sometimes, the absence of evidence becomes one of the most valuable results. Modern astronomy has also entered an era of precision cosmology. Projects such as the Dark Energy Survey, the Sloan Digital Sky Survey, and the Dark Energy Spectroscopic Instrument have mapped millions of galaxies across enormous volumes of space. These surveys do not measure the speed of light directly. Instead, they test the large-scale predictions of general relativity and cosmology. If the underlying laws governing light and space-time differed from current theory, subtle discrepancies might gradually emerge in the growth of cosmic structure or the expansion history of the universe. Thus far, observations remain remarkably consistent with Einstein's framework. The measurements continue narrowing the room available for alternative explanations. Meanwhile, a completely different revolution has unfolded beneath Earth's surface. The Large Hadron Collider, located near Geneva, accelerates particles to energies approaching those present shortly after the Big Bang. Its purpose is often associated with discovering new particles, and indeed the detection of the Higgs boson in 2012 represented one of the great triumphs of modern particle physics. Yet the collider also provides crucial tests of relativity and quantum field theory. Every collision probes how particles and fields behave at energies far beyond everyday experience. If hidden mechanisms influence the propagation of light or the structure of space-time, subtle departures from established theory might appear within these experiments. To date, no such departures have been confirmed. Instead, the Standard Model has continued demonstrating extraordinary predictive power. This success is both satisfying and frustrating. Each successful experiment strengthens confidence in existing theories. At the same time, it leaves less room for the new physics many researchers hope eventually to discover. Perhaps the most dramatic observational advance of the 21st century has come from gravitational wave astronomy. The twin LIGO observatories in the United States, joined by Virgo in Europe and Kagra in Japan, measure changes in distance smaller than the diameter of a proton. These instruments detect ripples in space-time generated by colliding black holes and neutron stars. Their sensitivity is almost beyond ordinary imagination. The 2017 neutron-star merger became particularly important because it inaugurated what astronomers call multi-messenger astronomy. For the first time, scientists observed the same cosmic event through gravitational waves and electromagnetic radiation. Instead of relying upon one cosmic messenger, they received several, each carried complementary information. Together, these signals provided one of the strongest tests yet that gravitational waves and light propagate consistently with general relativity over cosmological distances. Future observations promise even greater precision. Every additional neutron-star merger becomes another experiment performed naturally by the universe itself. Closer to home, advances in atomic clocks continue pushing precision toward extraordinary levels. The newest optical lattice clocks compare frequencies with uncertainties approaching 1 part in 10 to the 18th. To appreciate this achievement, imagine a clock that would neither gain nor lose a single second over a period longer than the current age of the universe. Although no real clock remains perfectly isolated for such unimaginable durations, this comparison conveys the astonishing precision now achievable. These clocks allow physicists to test whether fundamental constants drift over time. Even tiny variations could eventually reveal deeper layers of physical law. So far, nature continues displaying remarkable stability. Computer simulations have become another indispensable instrument. Unlike telescopes or particle detectors, simulations do not observe nature directly. Instead, they allow researchers to calculate the consequences of known physical laws under conditions impossible to reproduce experimentally. Supercomputers model galaxy formation, black hole mergers, neutron star interiors, and the evolution of the early universe. When observations disagree with simulations, physicists learn that either important physical ingredients are missing, or certain assumptions require revision. The dialogue between observation and computation has become one of the defining features of modern astronomy. Even artificial intelligence has begun contributing to this effort. Machine learning systems help identify rare gravitational lenses, classify galaxies, detect gravitational wave signals buried in noise, and search for subtle patterns within enormous astronomical surveys. Importantly, these systems do not replace scientific reasoning. They assist researchers by revealing structures that might otherwise remain hidden within overwhelming quantities of data. The interpretation still belongs to physics. Perhaps the most striking lesson emerging from all these instruments is not that they have answered every question. It is that they have dramatically narrowed the possibilities. Every new telescope, every improved detector, every more precise atomic clock, every particle collision, every gravitational wave observation, each quietly reinforces the remarkable consistency of the known laws of physics. Yet none has revealed the deeper origin of the speed of light. Instead, the frontier has moved. Scientists now know far more clearly where existing theories succeed. They also know far more precisely where those theories remain silent. The remaining questions no longer arise from a lack of measurement. They arise because even our finest measurements have reached the boundary of what current theories can explain. Beyond that boundary lies one of the most fascinating landscapes in all of science. Not a region filled with certainty, but one defined by carefully measured ignorance. There is a quiet moment that arrives in every mature science. It is the moment when researchers realize that improving the precision of their measurements is no longer enough to answer the deepest questions. For centuries, better telescopes revealed more stars. Larger observatories uncovered distant galaxies. More powerful microscopes exposed increasingly smaller structures within matter. Each improvement seemed to promise another layer of understanding. Sometimes it delivered exactly that. Sometimes it revealed something unexpected. The mystery surrounding the speed of light has now reached a similar point. Modern physics can measure this constant with astonishing accuracy. It can predict how light bends around galaxies. It explains why moving clocks tick more slowly. It describes the behavior of lasers, atoms, black holes, and expanding space with remarkable success. Yet when asked why the universe possesses this particular causal limit instead of another, the theories become noticeably quieter. This silence does not arise because physicists have stopped searching. It arises because they have reached the present edge of what observation can distinguish. One of the greatest challenges concerns energy. Many of the ideas seeking a deeper explanation for spacetime involve physical processes expected to become important only near what is known as the Planck scale. This scale lies unimaginably beyond the reach of current technology. The Planck energy is roughly 100 quadrillion times greater than the energies produced by the Large Hadron Collider. Even humanity's most powerful particle accelerator explores only a tiny fraction of this domain. Reaching the Planck scale directly would require an accelerator so enormous that practical engineering, available energy, and even the curvature of Earth's surface become insignificant compared with the required size. Some rough estimates suggest that a conventional circular accelerator, capable of reaching such energies, would vastly exceed the dimensions of our planet. The exact design would depend on technologies not yet invented. For now, direct experimental access remains beyond reach. As a result, researchers must search indirectly. Instead of recreating Planck-scale conditions in laboratories, they examine the natural experiments performed by the universe itself. Black holes, neutron stars, the earliest moments after the Big Bang, ultra-high-energy cosmic rays. Each offers a glimpse into environments far more extreme than anything humanity can build. Yet even these cosmic laboratories possess limitations. The interiors of black holes remain permanently hidden behind event horizons. General relativity predicts that information from within the horizon cannot reach outside observers. No telescope, regardless of future technological advances, can directly observe conditions near the classical singularity predicted by Einstein's equations. Whether singularities truly exist, or whether quantum gravity ultimately replaces them, remains unknown. Nature has placed a boundary around one of its most interesting environments. The earliest universe presents a similar challenge. The cosmic microwave background allows astronomers to observe conditions approximately 380,000 years after the Big Bang. When the universe became transparent to light, Before that time, ordinary photons scattered repeatedly through hot plasma. Electromagnetic observations cannot see farther back. Other messengers, such as gravitational waves or neutrinos, may eventually provide additional information about earlier epochs. For now, however, the first moments of cosmic history will remain only partially accessible. The region where quantum gravity may have played its greatest role lies largely beyond direct observation. Computer simulations encounter another limitation. Modern supercomputers perform calculations involving billions or even trillions of variables. They simulate galaxy formation, turbulent plasma, black hole mergers, and quantum interactions with astonishing sophistication. Yet simulations always depend upon underlying equations. A computer cannot discover a new fundamental law simply by calculating the consequences of existing ones. If the equations themselves become incomplete under extreme conditions, simulations faithfully reproduce those limitations. They magnify knowledge. They do not replace it. Theory faces its own obstacles. General relativity and quantum mechanics each possess extraordinary internal consistency. The difficulty arises because they describe reality using profoundly different mathematical languages. General relativity treats spacetime as a smooth geometric continuum. Quantum mechanics describes probabilities, operators, and quantized fields. Each framework succeeds brilliantly within its own domain. When both become equally important, neither remains fully sufficient. Attempts to combine them often produce infinities or mathematical inconsistencies requiring new ideas. This is why a complete theory of quantum gravity has remained elusive despite decades of effort. String theory offers one possible route. Loop quantum gravity offers another. Causal dynamical triangulations, asymptotic safety, causal set theory, and several additional research programs pursue different paths. Each captures certain desirable features. None has yet emerged with decisive experimental confirmation. The absence of evidence does not imply that these approaches are incorrect. It simply means that nature has not yet indicated which, if any, reflects reality. Measurement itself introduces another subtle limitation. Every physical observation requires interaction. To measure light, one must detect photons. To measure particles, they must interact with detectors. To determine the position of an object, some physical signal must reach it in return. There is no observation without exchange. At extremely small scales, the act of measurement becomes inseparable from the quantum systems being observed. This principle, expressed in different ways throughout quantum mechanics, places fundamental limits on what can be known simultaneously. It does not prevent science, but it reminds us that observation is always a physical process rather than a detached act of viewing reality from outside. Even language begins to struggle. Words such as before, after, inside, outside, space, and time evolved to describe human experience. They work beautifully for forests, rivers, mountains, and planets. They become less reliable when discussing quantum spacetime near the Planck scale. If spacetime itself emerges from deeper physics, asking what existed before spacetime may resemble asking what lies north of the North Pole. The question may require concepts not yet developed. Physicists therefore proceed carefully. They distinguish between meaningful scientific questions and questions whose current wording may already assume too much. This intellectual discipline is one of science's quiet strengths. It recognizes that sometimes the limits belong not only to technology but also to our conceptual framework. Another uncertainty concerns the constants themselves. The speed of light, Planck's constant, Newton's gravitational constant, and the elementary electric charge all appear fundamental within today's theories. Are they truly independent? Could they emerge together from a deeper structure? Could some eventually be shown to depend upon others? Or do they simply represent basic facts about our universe that admit no further explanation? No experiment presently answers these questions. Some philosophers of science argue that every chain of explanation must eventually end with fundamental principles accepted without deeper cause. Many physicists remain hopeful that future theories will reduce the number of independent constants by deriving them from more basic relationships. Both viewpoints acknowledge the present uncertainty. Neither possesses decisive evidence. This distinction matters. Hope is not evidence. Elegance is not evidence. Mathematical beauty is not evidence. Observation remains the final judge. Perhaps the greatest uncertainty of all concerns whether humanity is even asking the right question. History offers many examples. Astronomers once asked why planets trace circles around Earth. The deeper answer required abandoning Earth as the centre. Physicists once asked how objects move through the ether. The deeper answer required abandoning the ether itself. Future generations may look back upon today's questions about the speed of light in a similar way. The mystery may not lie in the constant. It may lie within assumptions that current physics has not yet recognized. If so, the next great breakthrough will not simply supply another equation. It will change the way we frame the problem itself. Until then, uncertainty is not a sign of failure. It is evidence that science remains alive. Every unanswered question marks the boundary between what humanity has discovered and what still waits beyond observation. And beyond that boundary, the next chapter of this story is only beginning. Every generation inherits a different horizon. For ancient astronomers, the horizon was the edge of the visible sky. Beyond it lay myths, speculation, and questions that no instrument could resolve. The invention of the telescope moved that boundary outward. Galaxies replaced stars as the great unknown. Radio astronomy uncovered an invisible universe. Spacecraft carried instruments beyond Earth's atmosphere. Gravitational wave detectors revealed a form of cosmic communication that had existed since the birth of the universe, yet remained unheard until the 21st century. Each advance answered questions that earlier generations could scarcely ask. Each also revealed that the horizon itself had simply moved farther away. The mystery surrounding the speed of light now stands at such a horizon. Physicists no longer wonder whether light has a finite speed. That question has been answered beyond reasonable doubt. They no longer debate whether every inertial observer measures the same value. More than a century of increasingly precise experiments has confirmed Einstein's insight with extraordinary consistency. The frontier has shifted. The question has become whether this constant is truly fundamental, or whether it emerges from principles that have not yet been discovered. Crossing that frontier will require something more than another decimal place of precision. It will require new ways of observing reality. One promising path lies in gravitational wave astronomy. The detectors operating today, remarkable though they are, represent only the first generation of this new science. Future observatories are expected to become dramatically more sensitive. The planned Laser Interferometer Space Antenna, or LISA, will place 3 spacecraft millions of kilometers apart in heliocentric orbit, forming an enormous triangular interferometer in space. Freed from many of the seismic disturbances affecting ground-based instruments, LISA will observe gravitational waves with much longer wavelengths than those detectable on Earth. Instead of listening primarily to collisions between stellar mass black holes, it is expected to detect mergers involving supermassive black holes, compact binary systems, and possibly signals originating from processes that occurred in the early universe. If traces of new physics influenced spacetime shortly after the Big Bang, gravitational waves may preserve information inaccessible through ordinary light. This possibility remains uncertain. No one knows exactly what such observations will reveal, yet they offer one of the few observational windows capable of probing epochs that electromagnetic astronomy cannot directly reach. Another frontier involves the next generation of terrestrial observatories. Projects such as the Einstein telescope in Europe and the Cosmic Explorer in the United States are designed to extend the reach of gravitational wave detection far beyond current capabilities. With greater sensitivity, they will observe vastly larger populations of neutron star and black hole mergers. Every event becomes another natural experiment testing the behavior of space-time under extreme conditions. The cumulative precision of thousands of observations may eventually reveal subtle departures from present theory, or strengthen confidence that Einstein's description remains accurate, even under the most demanding circumstances. Astronomy itself is also entering a new era. The Vera C. Rubin Observatory, with its wide-field survey of the southern sky, is expected to record enormous quantities of astronomical data, repeatedly imaging the visible universe over many years. Combined with future observatories such as the Nancy Grace Roman Space Telescope, these surveys will measure gravitational lensing, galaxy evolution, and cosmic expansion with unprecedented precision. Although these projects are not designed specifically to explain the speed of light, they will test the underlying framework within which that constant operates. Sometimes, understanding one mystery depends upon measuring another with greater accuracy. The same principle applies to particle physics. Researchers continue exploring possibilities beyond the standard model. Some hope to discover new particles. Others search for previously unknown symmetries. Still others investigate whether tiny violations of established principles might emerge only at energies or precision levels not yet explored. So far, relativity and quantum field theory continue passing every major experimental test. If deeper physics exists, it appears remarkably well hidden. That realization has encouraged many theorists to look not only toward larger instruments, but also toward new ideas. One increasingly influential perspective suggests that information may play a more fundamental role than previously imagined. This possibility has grown from several independent developments: quantum entanglement, black hole thermodynamics, the holographic principle, studies of quantum error correction. None of these subjects directly explains the speed of light, yet together they hint that space-time, geometry, and information may be connected more deeply than 20th century physics originally suspected. The holographic principle offers an instructive example, inspired largely by studies of black holes. It proposes that the information describing a region of space may, under certain circumstances, be represented by information residing on its boundary. This idea has achieved rigorous mathematical realization in specific theoretical settings, particularly through the correspondence known as CFT. However, whether similar principles describe our own universe remains an open question. Even within theoretical physics, careful distinctions remain essential. Successful mathematical models are not automatically descriptions of physical reality. Observation must eventually decide. The search for quantum gravity represents perhaps the most ambitious frontier of all. Its goal is not simply to combine two existing theories. It seeks a framework in which quantum mechanics and space-time emerge naturally from a common foundation. Whether that foundation ultimately involves strings, loops, quantum information, causal structures, or something not yet imagined remains unknown. Each proposal captures part of the problem. None yet captures the whole. This uncertainty should not be viewed as discouraging. History suggests that the most important scientific revolutions often occur only after researchers have learned enough to recognize the precise limits of their current understanding. Before Newton, the motions of planets appeared disconnected from falling apples. Before Maxwell, electricity and magnetism seemed unrelated. Before Einstein, space and time appeared entirely separate. Each revolution united concepts that earlier generations had considered independent. Perhaps another unification still awaits discovery. If it comes, its implications could extend far beyond explaining the speed of light. A deeper understanding might reshape our conception of matter itself. It could reveal why particles possess their observed masses. It might clarify the relationship between gravity and quantum mechanics. It could illuminate the origin of space-time or the earliest moments of cosmic history. Perhaps it would explain why the fundamental constants possess their observed values. Or perhaps it would reveal that some questions we currently ask require entirely new language before meaningful answers become possible. These possibilities remain speculative. Science has not reached them. It has only identified the direction in which they may lie. That distinction deserves constant respect. The boundary between established knowledge and informed speculation is not an obstacle. It is the place where science remains most honest. The speed of light continues to occupy a remarkable position along that boundary. It is one of the best measured quantities in all of physics. It is one of the most successfully explained within existing theories, and yet its ultimate origin remains unknown. Few scientific questions combine such extraordinary confidence with such profound uncertainty. Standing at today's frontier, humanity possesses telescopes capable of seeing galaxies whose light began its journey more than 13 billion years ago. We have detectors that measure distortions in space-time smaller than the width of an atomic nucleus. We build clocks so precise that they redefine the meaning of time itself. We model entire universes inside supercomputers. And still, One familiar constant quietly reminds us that understanding how nature behaves is not always the same as understanding why nature is the way it is. Perhaps that is the true edge of knowledge. Not the place where science ends, but the place where every reliable answer becomes the starting point for a deeper question. The journey began with a number that seemed almost too familiar to deserve another thought. Nearly every student of science eventually learns that light travels through the vacuum of space at approximately 299,792, 458 meters per second. It appears in textbooks, equations, engineering, astronomy, and countless conversations about the universe, like so many constants in nature. It quietly settles into the background of our understanding. At first, it feels complete, yet over the course of this journey, that single number has slowly changed its character. It is no longer merely the speed at which sunlight reaches Earth, or the pace at which distant galaxies reveal themselves to our telescopes. It has become something far more profound. It marks the boundary between cause and effect. It shapes the geometry of space-time. It determines how the history of the cosmos unfolds before our eyes. It quietly governs the conversations between stars, galaxies, and black holes. Even though none of them has ever paused to consider it, perhaps the most beautiful realization is that the speed of light tells us surprisingly little about light alone. Photons simply follow the rules written into reality. They do not create those rules. In Einstein's picture, they reveal the geometry of space-time. In Maxwell's equations, they arise naturally from the electromagnetic properties of the vacuum. In quantum field theory, they emerge as excitations of a field extending throughout the universe. Each framework deepens our understanding. Each explains a different aspect of the same phenomenon. Together, they form one of the most successful descriptions humanity has ever constructed. And yet, beneath that success, a quiet question remains. Why should reality possess precisely these properties? Throughout history, science has often followed this pattern. Questions that once appeared impossible gradually became ordinary. The motions of the planets were once mysterious wanderings across the heavens. Gravity united them with the falling of an apple. Electricity and magnetism once seemed unrelated curiosities. Maxwell revealed them as different expressions of a single field. Space and time appeared separate until Einstein showed that they belonged to one continuous structure. Every great advance has done more than answer a question. It has changed the question itself. Perhaps that is why the remaining mystery surrounding the speed of light feels so compelling. It does not merely ask for another measurement or another equation. It asks whether our present way of describing reality is the deepest one available. Modern physics answers many questions with extraordinary confidence. The constancy of the speed of light has been confirmed by laboratories, particle accelerators, pulsars, gravitational waves, satellite navigation, and observations spanning billions of years of cosmic history. These are not fragile ideas resting upon a handful of experiments. They are among the strongest conclusions science has ever reached. At the same time, honesty requires recognizing where confidence ends. No accepted theory presently explains why the universe possesses this particular invariant speed rather than another. Several promising ideas seek deeper explanations. Some investigate the quantum vacuum. Others explore emergent space-time, hidden symmetries, quantum gravity, or additional dimensions. Each contributes valuable insight. None has yet earned the authority that only repeated experimental confirmation can provide. This distinction between knowledge and possibility is not a weakness. It is one of the quiet disciplines that has allowed science to progress for centuries. The universe has often proved stranger than intuition expected, but never because evidence was ignored. Instead, evidence patiently reshaped intuition. There is something deeply reassuring in that process. It reminds us that uncertainty is not an empty space waiting to be filled by imagination. It is a carefully mapped frontier. Beyond it may lie answers that future generations will regard as obvious. Or perhaps entirely new questions will emerge that we cannot yet articulate. Our own place in this story is surprisingly modest. Human civilization occupies only an instant within cosmic history. The oldest light reaching modern telescopes began its journey long before Earth existed in its present form. The galaxies scattered across the observable universe have evolved over billions of years according to laws that remained unchanged while continents drifted. Species appeared and disappeared, and countless civilizations rose and fell. against that immense backdrop. The effort to understand a single physical constant might seem almost insignificant, yet perhaps it is exactly the opposite, because hidden within that constant is a remarkable truth about human curiosity. We are a species living on a small planet orbiting an ordinary star near the edge of one galaxy among hundreds of billions. And still we ask why the universe possesses the structure that it does. We build telescopes that gather ancient photons. We construct detectors capable of measuring distortions in spacetime smaller than an atomic nucleus. We compare clocks so precise that they challenge our ordinary understanding of time itself, not because such knowledge changes the sunrise tomorrow morning, but because understanding has become part of what it means to be human. Every generation receives the universe as an unfinished conversation. The answers inherited from earlier centuries become the starting points for new questions. Maxwell inherited electricity and magnetism. Einstein inherited Maxwell. Modern cosmology inherited Einstein. Future physicists will inherit today's unanswered mysteries. Among them, the origin of the speed of light will almost certainly remain one of the most profound, whether its explanation ultimately lies within quantum gravity, emergent space-time, deeper symmetries, or an idea that has not yet been imagined. No one can honestly say. For now, the evidence carries us only so far. Beyond that point, science waits, patiently, carefully, open to surprise but unwilling to mistake possibility for fact. Perhaps there is something quietly fitting about ending where we began. The speed of light still appears in our equations as the same familiar number. Nothing about its measured value has changed during this journey. What has changed is the way we see it. A simple constant has become a doorway into questions about space-time, quantum fields, gravity, information, causality, and the origin of the cosmos itself. The number remained the same, our perspective did not, and somewhere beyond the reach of today's telescopes, beyond the limits of our most powerful accelerators, and perhaps beyond the mathematical language we currently possess, the deeper reason for that number may already exist, waiting with the same quiet patience that the universe has always shown. Until then, one final question remains suspended between everything we know and everything we have yet to discover. If light has been revealing the structure of reality since the first stars ignited, what deeper truth has it been quietly carrying all along?